So this is part two of our blueprint discussion. We've already gone over the basic features of every blueprint, from the title block to the basic dimensions, revisions, notes, views. So in this next video, we are going to continue, and we're going to start off talking about designer's intent. And the the reason designer's intent is something I want to talk about is because a blueprint is a collection of requirements that one or more people probably spent a lot of time and energy trying to document. And they have to take a 3D idea, a model usually, or some other way of coming up with their design and put it down in a two-dimensional form. And sometimes that can be really difficult to do. This example that I've shown you in this video is pretty basic, but this part has no function other than teaching, but some other parts have real functions, and they get more and more complicated as you're trying to add features and also reduce costs, and you look at the entire design, and something very complex can come out of something that's very basic, that started off just as an idea, but when you have to put it on paper, things can get a little more complicated. So as inspectors, someone who's reading a print needs to understand it. You're not going to have all that nice background of what the part does, how it was generated, what the function is. All you've got is the black and white requirements. And oftentimes prints are confusing. I have an engineering degree. I've been an engineer, created blueprints, and it's challenging to try and satisfy all the customers that are involved, because you've got, you want the engineering perspective, but you've also got the supplier or manufacturing perspective, there's a quality perspective, there's a customer perspective, and you're trying to make something that satisfies all of these requirements. But usually what happens is you have to set a minimum standard for these requirements, and so sometimes when you do that, it leaves people wondering, this isn't usual. This doesn't make sense. So I've already kind of talked about, let's go into more discussion about these customers. So first of all, I break it down into three main customers. So you have the design or the engineering involved, and their key requirements are to define all the features of the part. At a bare minimum, you have to define the size and the location of every feature. That's all. And so many, I've been in situations, many engineers, that's all they need to do. How they achieve that goal is not as critical as completing it. So there are many different ways I could have done this print. I could have put the views in any location. I could have set the datums anywhere I wanted. I can call holes from the top side or the bottom side, from the left or from the right. I could do chains. I could do single origin datums. You can do unilateral dimensioning or bilateral dimensioning. We're going to go over that too later in this series, but there's a lot of options that we have, and so sometimes the bare minimum, you just need to define them. And then usually you're going to try to emphasize the key functional or the cosmetic features of the part. So what's most important will usually get the most attention. It could be the tolerancing of a feature that's used for assembly, the location of it, the size of it. Could be notes we've talked about, notes in the corners. So they'll usually focus on, an engineer will focus on, okay, what's critical? We'll put a lot of effort into defining that exactly the way we want it, and the rest of it doesn't get that level of critical thinking, and it meets that requirement of let's just define it. These are not critical features for the function of the part, so we don't have to put as much effort into defining them. And that's one way to do it, and that's a very pragmatic way to do it, to focus your efforts where you think they're needed most. That third bullet point there, from engineering or design perspective, manufacturing processes may or may not be defined, so that can be an area of confusion and even sometimes conflict, where the print has a tolerancing that may not be reflective of the manufacturing method's capabilities. Those are always discussions that should be had when a print has a requirement that looks like it's either going to be beyond the capabilities of the manufacturing process, which is not as likely. What's more likely is it's within the capabilities of the manufacturing process, but it's going to require excessive controls. It's going to be very expensive. And so because it can do it doesn't mean necessarily you shouldn't change the requirements to be more reflective of economical manufacturing. So sometimes a process will say, look, we want you to grind this, we want you to turn this, we want you to use a certain, for example, certain heat treating process, whatever it may be. Sometimes it may be defined. Most of the time it won't be. The process won't be specified. It'll be up to the supplier, which gives the supplier flexibility. But what's kind of goes unstated sometimes is when you're using a title block tolerance, like in this example, this title block is really geared towards a machined part, whether it's manual or CNC. It's not really applicable for any other type of manufacturing because of the tolerancing involved in the title block. So that almost defines the manufacturing method. And sometimes methods improve over time. New technologies emerge like 3D printing, where things are cheaper to 3D print than to machine, but the prints don't get updated. And the prints still say, have these machining tolerances or whatever. It's normal. It happens in almost every industry I've seen that, sometimes the prints lag behind the technology. And, hopefully that's not the case for you. But if you think like, hey, we could make this part a different process, may not hold all the requirements on the print, but we think it's going to satisfy the function. Sometimes you can work with that, get some new requirements around this new process you're going to do. So that leads me into the number 2 customer, production or suppliers. What are their requirements? Well, their requirements to basically, is all the information on there to satisfactorily make it? That goes back into the first bullet point for design, right? If you get a print and there's features on here that are not fully defined, that you're like, there's some missing information here. I don't know where this hole goes. I can see it on here, but there's no, I think it, maybe it's lined up with this other hole, maybe it's not. But at a minimum, production needs to know that. So, second of all, do we need extra internal or intermediate requirements to achieve the final requirements? So sometimes, like this part, certainly would require multiple operations in most manufacturing processes. Couldn't do all of it in one operation. The best you could probably do is 2. But I know from how, I'm thinking this is at least a 3 or 4 operation, just because we have features on many sides. So sometimes, there may not be some GD&T like flatness or parallelism on this print. I made this print fairly basic, didn't want to overload it with GD&T. But in order to achieve the other features, your intermediate, your operation 1 might say, look, we need to keep this flatter than the print requires in order to achieve operations 2, 3, and 4. So even though it's not on the print, sometimes it becomes a part of the work instructions or the job traveler. So that's what production is going to look at. They're going to look at this part and they're going to say, okay, how are we going to achieve all of these requirements? And that can go into why you really need a good print, because manufacturing is going to be asking itself, how can I achieve the requirements to make this? And they may, I just mentioned cost, Well, all these, like maybe keeping things extra flat, extra parallel is increasing cost. And at the end of the day, when the part's finished and the function, maybe a couple of these tolerances can be opened up to allow for cheaper manufacturing. Just a couple, not all of them, but the key ones that are driving cost may not matter to the final function. So the production people are going to be thinking about that. They're going to be striving to achieve these requirements because they don't know what the part does for sure. Most of the time you can infer, but you can't know for certain sometimes. And then let's go into that third customer, inspection or quality. So our only driver is really, does the part pass all final requirements via the direct methods when possible? So, I always say, again, the print has all the requirements. Inspect to the print. Don't inspect to what you think the part does or what you think the requirement should be. The print is the requirements document. So if they call a hole from the bottom up to the top, check it from the bottom up to the top. That's a direct method. If they call it, from the right side over, check it from the right side over. Don't go from the other side. And we're going to get into why, but if the part has to be maybe registered from the bottom surface, I'm sure, hopefully the engineer tolerance that way for a reason, and that they don't retolerance it from the top for another reason. So it's better as inspectors to verify as much to print as you can, because you're assuming that, as I talked about, the engineer is putting a little bit of effort into defining not just that basic requirement of everything's defined, but a little bit of the function. So if you can, emulate the function you see on the print by checking it the same way it's called out. If everything is made exactly at nominal, right, it wouldn't technically matter. You could use shop math, but in reality, it's never made exactly on nominal. So you're going to risk making a mistake. Bringing in shop math always introduces a little extra complexity and risk making a mistake. So if you can do it directly from the print, you're going to have more confidence in your measurement. And I would say the videos that might go speak to this a little bit more are going to be the surface plate stuff, and maybe the hole inspection. With calipers, with micrometers, with some basic tools, they're so limited that there's not a lot of choice in the matter. But with surface plate, you get a lot of options with how you're going to set up the part. CMM as well, how you're going to measure the part and call it out. So as much as possible, go after that most direct method. And then here we're going to continue this sort of discussion about prints and the people involved and the designer's intent. So first of all, prints are a contract between all parties, right? Design writes the contract, production must conform to the contract, and inspection or quality enforces the contract. So it's very important that this contract is written up well. I mean, when you do a root cause analysis on anything, you start thinking about, well, what's the root of this? The root is the print or the 3D design. But as I mentioned, you can make a print many different ways. And if the print starts off on a good foot, everybody else will follow along. But if the print starts out bad, it's going to be hard for production. It's going to make more work for quality as they're spending more time inspecting, not just because of bad parts, but also because these complicated callouts are requiring complicated fixturing and expensive and time-consuming inspections. So this is a contract. Everybody who is involved must adhere to it. And the blueprint is the ultimate authority. I bold and underline that one. It's the ultimate authority on all disputes and discrepancies. So oftentimes, I've mentioned it before, sometimes I say, check your process plan, check your inspection plan, ask somebody, talk to an engineer, but in reality, the black and white is what's the ultimate authority. And if you're going to get a change, I've mentioned talking about loosening tolerances because of manufacturing. Document it. We call it a red line. Get a red line on your print, which is where an engineer or somebody who has the authority to make a change will cross out a dimension in red, put the new dimension or tolerance, sign it, and initial it. That's the most basic form. You can, every company might have different policies on red line. It's usually an engineer, and it might even be the person who's in charge, that the only one that can make the decision. So you can get revisions, you can ask for revisions, and then hopefully, first of all, have a good reason. It should usually be revolved either around final quality or performance or cost, right? Those are the three areas where companies are willing to listen on cutting costs, improving quality, or improving performance. Throughout my career, I've looked at prints and I've said, look, I know what this part does, but this print isn't reflective of what the part does. If I inspect it the way you're asking me to, it's ignoring some potential issues. Why don't we change the print? All we got to do is just change the call out from this style to this style. It'll be more reflective of what the part does. It will help us catch problems. It'll focus production on the actual critical nature of this part instead of looking like it's not critical because you have it dimensioned this other way, this very basic way. And that's something that comes with skill, comes with experience, and sometimes it's product knowledge. There will be many people watching this video who's, you're working in a job shop and you don't know what the part does. You're just given this from another company, and it's your job to make it or inspect it. So, but you can have those discussions if you feel like there's a reason. So I mentioned some other documents that work hand in hand with these. These are the ultimate authority, but your work instructions will also have maybe fixturing instructions, tools to use. Your inspection plans might have fixtures to set up again, methods to use, specific instructions. But again, the print is still the authority. And then your purchase orders, when you're working with vendors, purchase orders will usually have some requirements. They may not always have prints. So when you're watching this video series about blueprints, you may not actually have a print. You may have some other requirements, but everything I've talked about, it's just requirements. This is a requirement sheet in graphical form, but any requirements, these principles apply. And then, I mentioned it a few times, inspecting to print. What is inspecting to print? It comes with a choice. So do you inspect it directly or do you use shop math? And my rule of thumb, what I recommend inspectors do is always inspect the print when possible. Like I said, if they call it from over here to over here, check it that way. If your datum is, if your datum is on the bottom of the part, take all your measures off the bottom of the part. If your datum is on the side, take them off the side. Try not to involve shop math unless you have to, but I'm not saying don't use shop math. I use it all the time. It's a necessary tool, but it involves adding a little more complexity. When you have to use shop math, you usually have to measure a few features like a diameter to get a radius, an overall thickness to get a step depth. You're doing some subtraction with other features and you're adding some complexity because of the error that stacks up. So as much as possible, inspect it to print. And once again, I mentioned the surface plate video is really where we get into setting up fixtures and inspecting directly to print. For hand tools, it's a little more direct. With hand tools, you still mimic the print and use as little shop math as you can. And why? Well, this, it reflects the designer's intent. I mentioned you can set datums anywhere you want when you're a designer, and if you're just looking at this in a vacuum, completely by itself, like this part, they could put the datums anywhere they want. They can call the locations from anywhere, but they've actually chosen something. Hopefully they've chosen something that makes sense, that gives a little bit more insight into how the part works. Otherwise, there's an auto dimension feature in most CAD softwares. The last time I saw it was like 8 years ago, so I know it's available, where you can take a 3D model and it'll auto create the dimensions for you in a second and spit out a print for you, and it will only satisfy that very first requirement of define all features of the part, but there's no extra little communication about what the part does that way. It only helps you make the part and define the tolerances, but when prints are done well, you'll get a little bit of insight into how the part functions, which will increase your odds of making the part correctly and passing the inspection. So this has been a little bit of an aside from blueprints, but I've been an engineer, I've been an inspector, so I know I've seen both sides of it. And as an engineer, I usually try to satisfy the requirements of everybody. It's usually possible to find a print that not only satisfies the manufacturing method you're going to use, the inspection method you're going to use, and the design. But oftentimes it just doesn't happen. When I said I've been on the inspection side of it, and I've gotten a lot of prints that really don't make sense for inspection or don't make sense for manufacturing, and you're talking to the machinist and you're looking at the print and you're just like, what is this? What were they thinking? And it's okay. Sometimes they're not. It's a lot of work to look at the whole picture on every single print you do. So I understand, but hopefully, if you listen to the feedback of production people, they'll usually give you a better way to do things that's less effort and more cost effective. So that's my little aside from being an inspector for 5 years and having also been an engineer. I know it's difficult, but it is possible. So when you're inspecting to print, some questions to consider, when you're looking at it, well, what tools do I need? What fixturing setup do I need? You should always be using the print as your guideline for making these decisions. So the print and the tolerance. So you're looking at the datums and where things are called, as well as the title block tolerance or the specific tolerance next to the feature. So if you shouldn't just be looking, what I should never do is take this print, set it aside, look at the part, and decide how I'm going to measure it. You don't do that. You need to know your requirements. Now maybe you've got like the world's greatest, most accurate optical CMM and nothing beats it, but most of the time you're going to have to use this as a guideline. When can you use your calipers? When do you need to use a height gauge? When do you need to use a micrometer? There's always a trade-off. When can you use pin gauges? When can you use a hole mic? How accurate do you need? We watched the other videos about tools, and I'll go into the accuracy of each one, situations when you can use them. But the situation is always tolerance driven, okay? So remember that. You always look at the print to figure out how you're going to set up your fixture and tooling. And then the second question, I've just spent about 10 minutes on it, is why is it called this way? If a direct measurement, like I've always said, do a direct measurement, but if it's easier to do an indirect measurement, sometimes you go that route. If a direct measurement is you feel like it's not very repeatable, like you couldn't set it up twice and get the same result, if it's going to take you an hour and it's probably not going to be any more accurate than an indirect one, use that trade-off to do it. When in doubt, go direct, but if you start to have some doubts, think about going an indirect method. Ask yourself which is harder or riskier. Risk is a big part of quality control. In some of the other videos, I'll talk about, when we talk about sampling, when we talk about uncertainty ratio, all of these topics involve risk. Every measurement I do has an element of risk that I'm either going to pass a good part, or sorry, I'm either going to pass a bad part, or I'm going to reject a good part. No matter what we do, that possibility is always there. And this video series is kind of designed to help you make the right decisions to minimize those odds, but they're always there. So when you start adding more complexity, you add more risk. You start adding shot math, you add a little bit more risk. As 5 years in an inspector, I've done it myself. I've seen other inspectors do it. They use a shot math technique. Part looks like it's fine. Maybe the direct measurement was one that we thought it was too complex, it was too much work, and you think, okay, well, I'm going to do it this indirect way, and later on it bites you. If it turns out the part didn't work, something in your shot math, something in that shortcut, that sort of shortcut you took, there was something wrong with the part you didn't know about, and you were using it as part of your inspection. You may have used this bottom surface and assumed it was flat and parallel, and you're coming off of the edge to get this hole, and turns out, hey, it was actually a U shape, and you didn't get a good reading, and you made an assumption that it was flat, and it ended up biting you. So there's always risk. Whenever you use shot math, make sure to check your assumptions about the other features you're using, but inspect the print when you can. That's all I'll say. So like for this one, let's take this sidewall for example. Let's take a look at it here. This side slot is 500 from the back face, which is datum A. It's not 500 from the top face, and the slot width has quite a lot of open tolerance. The slot width is 0.38 plus or minus 10 thousandths. So there's a lot of areas where there's a lot of range where the sidewalls of that slot could be, and even though it's a simple setup, I would rather check it from the back face like the print is calling. You can use your fishbowl technique to determine that. I haven't demonstrated the fishbowl technique on video. So you take your part. I'm going to line it up with one of my views. I'm sorry about the quality of the video. Something about the shadows that doesn't make prints look good. But I'm going to hold up my front view the same way, and when I do a fishbowl over here, I can see that this back face is this back face. This little notch here is this little notch here. So if I'm going to measure the slot, I'm going to grab it from that face and do 313. The slot edge is 313, 314 from that face, and then I can use half of the slot width to figure out where the center is. There's some other fishbowl. So back here, I can back to the top. So now you can see these steps are aligned. The notch here is aligned. The slot is aligned. And if I wanted to get to the back side, I might start over here, 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 and there might be a view. There might be a backside view of if there were features on the backside that needed to be called out, there might be another view. And then I'll swing it back, and I'll swing it back, and then I could get this view by swinging it this way, and I can get this view, by swinging it this way. All right, so this is the fishbowl technique. All right, so let's jump back into our presentation. Sorry about this. Okay. So I mentioned shot math a lot, but we're going to do an example. Shot math is a all-inclusive sort of terminology. It means anytime you can't just take your measurement tool and get a direct measurement, that's a direct measurement. That has no shot math involved. But if you need to actually do some math, addition, subtraction, trigonometry, circumference sometimes, angles, angle subtraction or addition, triangles. If you're not good with triangles, you better be, because we're going to be doing a lot of triangles in inspection and circles. So here's an example. That 3/15 step thickness in the top view here, if you're going to measure that from the way it's called out, that's a simple caliper check from the back side. There's nothing involved. But let's assume for a second that this is being machined out of a piece of aluminum, and this is the operation that starts first. It goes around, it does the slots, and it's still in the machine. All right, the backside hasn't been cut yet. Now you want to verify operations 1's work. First article of operation 1. There's still a piece of uncut material on the backside, so you can't. Right? You can't verify anything back here. It's still in the machine and it still has extra material. So you're going to have to come off of the top and try to verify each step. Now, because this part is in process, these are all reference checks, but you can still use the shop math to know if you've already made a scrap part or not. So you look at that print and there's a thickness of 1 inch. So it's 1 inch thick overall, and we're looking for the 0.315. So 1 inch minus 0.315 is going to be 0.685. So it'll be 3/15 when it's finished. From there, and it will be, if I had a long enough gauge, it'll be 685 from the top surface. So 685 from here to here. That's shop math. So do I have anything? I've got a 1, 2, 3 block. This 1, 2, 3 block is at 0.999, so it's 1,000 short. And this is another example of shop math where I'm bringing in another fixture. Probably not recommended. There's other ways to do this, but I happen to have the caliper right here. I will flip this around so I can show the camera what I'm doing. So I should get an extra inch of thickness that I wasn't expecting. So I'm expecting 0.685, so I should be getting 1.685. And I'm doing my best. Here we go, 1.685, 1.686, okay? Let me show you on the second camera if you want to pull up the video feed of what I did. It's a little bit harder to hold it, but I can give it a shot. Oh, yeah, I should switch on the other camera. So I'm going to drop the depth bar real quick. 1.686. Okay, so we have a caliper video for you to watch if you're not sure what I just did. But this is a form of shop math. I didn't get a direct measurement. You know, again, I'm kind of assuming it's still in the machine. It's not finished yet. If data May is not cut yet, all of those features off of data May, I'm going to have to check another way. So I'm going to use shop math. Here's another example. I don't have this part. I do have the print. So one of the when you're looking at hole patterns, what you're going to see a lot of the time is going to be some sort of equal spacing between the holes. So here to here to here to here, all these 8 holes, they want them equally spaced. Now, some prints are going to have the angle. In this case, it would be 45 degrees. If there were more holes, that would be a smaller angle. If there were less holes, it would be a bigger angle. Some prints will call it out that way. Some prints will say equal spacing. And other prints might just say, you know, forget this equal spacing and angle nonsense. We're going to call it all an XY. We're going to define an XY coordinate in the corner, and we'll be done with it. You know, we'll do it all in XY. But any way you do this, you're going to need shop math. For one thing, as I mentioned in the hole videos, hole inspection videos, you can't register a gauge on the centers. You can only register your gauges on the sides of holes, not the centers, unless you're working with, a CMM can calculate the center for you. Some height gauges can calculate the center for you, but in reality, you're going to have to use the hole radius to verify the center point, which means knowing the diameter, knowing how out of round it is. That's a GD&T circularity requirement. You may need trigonometry. So there's a few tricks. I want to take a quick moment to, when you're talking about shop math, it's not just as simple as verifying numbers. What I like to tell people is there's often requirements that are supposed to be symmetric, and you can verify symmetry. Instead of verifying 45 degrees or XY coordinates, sometimes you can verify symmetry, and this is an example where you can. So if you go with your calipers, if you grab each hole to hole, you can verify that if all the hole to hole distances are correct and they're all the same, then it's symmetric. And if it's symmetric, it passes, right? Now, if it's not symmetric, how not symmetric is it? We don't know. Not without further calculation. But a lot of times if you have an open tolerance that allows, maybe plus or minus 5, plus or minus 10 would be better, but to use a caliper, if you got an open tolerance, these are not critically called out features, this is a more than acceptable way to do it. So I don't have that part up on the screen, but I do have this little one here. So I will try to demonstrate the same concept. So we're going to find out, are these 4 holes, are they centered? Are they equidistant from center? And are they equidistant from each other? It would be the same style as the print I showed you on the screen. But first of all, I'm going to verify if they're on center. So I'm going to grab hole to hole with my caliper, 236. This one, 235. This one, 235. This one, 235. So maybe even my first one was wrong. Another way you could do this is you could zero the caliper on one of your features and check that way. So I'll do this next check with that method. I'm going to zero it equidistant here, 508. It's a little bit hard to zero and show you what I'm doing, but okay. Now we're going to see how far from 0. I got 0 again. 0 again. If you've watched my caliper video, you'll know the technique I'm using is kind of rocking it and letting the smallest point grab onto it. So I had equidistant from center. I had equidistant from each other. I'm going to say this part's good, assuming I don't have a print for this one, but if it's the same type of tolerancing as this one here, I would say this part passes. It's symmetric. Symmetric verifies the requirements. So let's flip back and take a look at our presentation. So I did that with this other part. So like I said, when you bring shop math in, sometimes you are deviating from the nature of your contract and designer's intent. Sometimes you have no choice. So use your direct methods when you can, use the shop math when you need to deviate. Because sometimes it's the only thing you can do. I mean, realistically, if I don't want to use a CMM, this part is entirely round. It's going to be kind of hard to set up on a surface plate and do the shop math that way. I was able to verify it in less than a minute with a caliper, and if it's open tolerance, everyone's happy. So be confident in the substitute method that satisfies the stated requirements. So whatever shot math method you're using to substitute for the direct method, you need to have the confidence in that method, not somebody else. But do you feel confident it's meeting the requirements? Because you're the one making the decision, you're the one inspecting it. And if your method is better, easier, and has a higher confidence, you can try asking for a print change. This was not a good example of something I would ask for a print change, because I can't think of a way to call the print that makes sense for what I did. But with this milled part here, sometimes, hey, op 1 has all of the critical features on it, right? The part in this orientation, if I do an op 1, mill it, 3-axis mill it, get most of these features. Why isn't this data may? Is there a reason the back is data may? Is it actually, talk to your engineer, is there a functional reason this is data may? If there is, hey, leave it alone, right? The designer picked a good datum for the final form of the product. Maybe manufacturing should change their operations and do this first, but hey, I'm not going to be the one to say that. I'm just the inspector. But I've inspected probably in the thousands of parts where they put data may in last on like a 4 or 5 operation, and as an inspector, it's frustrating because you're doing shop math the entire time. You're doing all these substitution checks the entire time. At the very end, they put the final datum on, and you wish production would do it in the other order. You wish they would do data may first. So, but going back, forget that. Getting back on track. If you could change this to data may, well, then you could do direct depths of these steps, and that might be easier. That might make everybody happier. Machining will be happier. They'll be able to run the part in the order they want, and inspection will be able to get direct methods. And if it doesn't affect part functionality, hey, everybody's happy. Oops. Skipping ahead. Sorry about this little technical difficulty. All right. So before we move on, I'm gonna end the video here. I don't want it to get too long. We're gonna end in 3 parts, I believe. So I want to thank you for watching this video on print. Designer's intent and contract nature of it and shop math. I think these are all really important for an inspector to understand. Even if you don't understand, you're in the beginning of your career, you don't quite understand what I'm talking about. The more parts you see, the more prints you see, the more you move between a couple of companies and see different perspectives, I think this will make more sense to you. But if you're just now beginning, as I said, try to stick to those rules. Use the blueprint tolerance to drive your decision making on tools, and use the style of dimensioning to drive how you register your anvils, checking exactly the print, or if you need to use a shop method. So in the next video, we'll cover the important steps for inspecting a part against the print. I want to thank you guys for watching. Please check out my website, pragmaticmetrology.com, and please continue with the 3rd video as well. I have more videos up on the website covering many of the common gauges for machine metal parts as well as other industries. And I want to thank the Laney Machine Technology Program in Oakland for providing this part for me to use in this video. They provided many of the tools in the video series and parts as well. They're a really great program. I recommend, if you're in the Northern California, Oakland area, check out their machine technology website, where they've got classes on CNC machining, manual machining, quality control and inspection, metrology, CAD design, mechanical drives. They have a lot to offer anybody who's interested in a career in manufacturing. One of the more established colleges in this state in that sense. So that's Laney College, Machine Technology Department. They've got apprenticeships, they've got associate's degree and certificates you can earn. So it's a great place. Please check them out. I thank them for providing this part. And I thank you guys for watching. Please continue with our blueprint discussion and check out all my other videos. Thank you.